Hey guys, today we're going to look at projections. So there's two types of projections, scalar and vector. So we're going to take a look at scalar projections first. So the scalar projection, of the vector A onto the vector B is defined as, like this. Not everybody uses this notation. I think your textbook does not actually. I think it just uses words to describe it, and that's fine. It doesn't really matter. But we'll say, whoops, not and. Oh my goodness. Okay, so we want the scalar projection of A onto B. Okay, and we're going to define this as the absolute value of A, or the magnitude of A, I should say, cos theta, and that is where theta is the angle between A and B. So theta is the angle between vector A and vector B. Okay, and so what this means, and we get this diagram over here and you can see it. So what we want is we're finding this magnitude here, okay? This magnitude, okay? So you can think of it as just like shining a light on it, and this is kind of casting, it's projecting the shadow onto B, and just the length of that shadow, that's all it is. Okay, so let's do a quick little example here. So we've got, so magnitude of A is 10, magnitude of 16, or B is 16, and there's a 120 degree angle between them. Okay, so, whoops. So the scalar projection of A onto B is equal to, it's just going to be the magnitude of A times cos theta. Okay, so in other words, it's going to be 10 cos 120. Okay, which is going to give us -5. Okay, so there you go. So again, you'll notice it is a scalar. It's just the number, -5. Also, the reason it's negative, it makes sense if you look at the diagram here. Because our theta is greater than 90 degrees, it means that we're going to have, it's going to be going sort of in this direction. So it's actually casting down, onto the negative part of B. Like there is no B there, so you'd have to go into the negative. So that's why you're going to get a B, and that'll happen, or a negative, and that's what you're going to have that anytime theta is greater than 90. Okay. So I'm going to add this one. Just for brevity's sake, I'm going to have you do this one on your own. So I'd like you to actually pause the video, try it, and I'll tell you that you should get -8. Okay, so if you get -8, you did it right. Okay, so let's skip on to some special cases here. Some special cases. So if we have A and B are both collinear and going in the same direction, okay, so in other words, cos theta is going to equal 1. So if you're projecting the A onto B and they're going in the same direction, it's going to be just the magnitude of A is going to be the projection. Okay. Similarly, if they're collinear but they're going in opposite directions, you're just going to have the negative of the magnitude of A. Okay. And then, of course, if they're perpendicular, you think about it, you're not actually casting anything onto the projection or onto the B, so it's going to be 0. So that makes sense logistically and algebraically, because of course cos of 90 would be 0. Okay. All right. So if I want to find the scalar projection of a vector A onto itself, well, I mean, this makes sense. If you're projecting it onto itself, it's just going to be the magnitude of itself, right? You project, it's going, I mean, you think about it like a shadow. The shadow is going to line up exactly because it's exactly the same project, or exactly the same vector. Okay, and of course, opposite vector is going to be exactly the same, but it's going the other direction, so it's just going to be negative. Okay. All right, so let's take a look at the dot product in scalar projection. So this is the same thing. We're doing the same thing, but we're going to use dot products to calculate it. And this is actually a much nicer way to do it. I mean, dot products in general are kind of better a lot of the time. But anyway, so first of all, it's worth remembering. You need to remember, it's not just worth remembering, that we defined the dot product as the magnitude of A times the magnitude of B times cos theta. And you'll notice this looks pretty similar, okay? This looks pretty similar to that projection formula. And in fact, if we rearrange it just by dividing by the magnitude of B, okay, then you would get, on the right, I'm gonna switch the sides here, but on the right you would have A cos theta. Okay, so I've divided out the magnitude of B, and that's going to equal A dot B. I'm not sure why I put that in brackets, and divided by the magnitude of B. Okay, which this here was the same as the formula for scalar projection. So what this tells us is that the scalar projection of A onto B can be written, why is that green? It can be written just as A dot B divided by the magnitude of B. Okay, and again, we remember the dot product is a scalar number, so it's going to give us a scalar over top of magnitude, which is also a scalar. So we're left with a scalar. Okay. So if we have a Cartesian coordinate system and a vector A, which is ax, ay, az, the scalar projections of that vector onto the unit vectors I, j, and k are just going to be it's just going to project its components, right? So you project A onto I. So let's just write this actually. Let's just say S projection of A onto, oh, I'm actually skipping ahead, and this is, well, whatever. Onto I, okay? So if I project it onto I, okay, it's just going to give me, it's only projecting that X component, so it's just going to give me AX. Okay, so that's actually the answer to that one right there. So, okay. So in other words, what they are is just the AX, AY, and AZ, respectively. It's just those components. Those components project onto the different ones. Okay. So, oh, I guess I didn't do it here. So A onto I, so if I have this vector here, 2, -3, and 4, then it's going to just equal 2, because it's just the AX. Okay? It's just the first one, because we're projecting it onto the one in the X direction, the unit vector in the X direction. It's just going to project that component onto it. Okay? So, if I project it onto I minus j, okay, well this is going to give me, we're going to have A dot I minus j over the magnitude of I minus j. Okay, and this is just using our formula here. Okay, so we're going to write this in components. So we're going to say A is 2, -3, and 4. And then we have 1, -1, and 0. And the whole thing is over square root of 2. Okay? Because it would be, these are each, the magnitude of both I and j are 1. Okay? So 1 squared plus -1 squared is 2. Okay? So from there, we take the dot product of this one. Remember, you're just multiplying the x components, the y components, the z components, and adding them. So it's just going to give us 5 root 2. Okay? Now, of course, and I didn't do this when I did this before, but you, of course, remember that it is not considered proper form to give me a final answer that has a square root in the denominator, so we're going to rationalize that, which is just going to give us 5 root 2 over 2. Okay? All right. So I want you to do these next two on your own. And those ones we're just going to take up at the beginning of class. Okay? So let's skip ahead here. And I'm actually going to skip over this part. So don't worry about that right now. Or maybe ever. I'm not sure if we'll come back to it. I want to skip on to the vector projection. Okay? So the vector projection of the vector A onto B is a vector this time, obviously. Hence the name. And it's defined as, right, V of A onto, my writing's not doing so hot today. That's okay. All right, so it's defined as, you got the magnitude of A times cos theta. And what we want to do is we want to take, so that was obviously the scalar projection, and so it's the same idea, it's just that it's now a vector going in the direction of B. So what we're going to do is we're going to multiply it by vector B divided by the magnitude of B. So in other words, what we're doing is we're multiplying it by the unit vector in the direction of B. Okay, so that's what that is there. Okay? And so you can see over here on the diagram what it is. Okay, so it's exactly the same as before. It's got the same magnitude as the scalar projection here, but now I'm actually just adding this, direction to it. I'm saying, well, it's going in the same direction as B. Okay. All right. So, like before, we can write this using a dot product, which is usually the better way to do it. Not always, but usually. Oops. Okay, so it's the vector projection of A onto B. And we're going to do the same thing where we're just going to say, we're going to write out the OR formula, but we're going to multiply it by B over the magnitude of B. So the way I'm going to do that is I'm going to just add a B here. And on the bottom, because it already had the magnitude of B on the bottom, so now I'm multiplying by another magnitude of B, so I can actually just square it. Okay? And so again, you know that this is going to give us a vector, because right now, sort of this part and this part, those are going to be scalars. So you're basically just multiplying a scalar. You're not basically, you are just multiplying a scalar by a vector, which will, of course, give you a vector. Okay? All right, so again, note if we're doing if we're projecting the components of a vector, or a vector made of components onto the unit vectors, this time it's basically the same thing, but you're going to have it's going to project it as AX. So you take the X component of A, and it's going to go in the direction of I, which since I is already a unit vector, that's all you have to do. So Y would be then obviously onto the J, or AZ onto K. All right, so if you project A onto I, it's going to give you this. If you project it onto J, it's going to give you this. If you project it onto K, it's going to give you this. Okay? All right, so let's see. So let's try a couple here. All right. So there's A and B. I'm going to project A onto B. So I'm going to use the dot product version. So I'm going to say A dot B. I'm going to project that onto B and divide it by the magnitude of B squared. Okay. So if I do that, I've got the dot product of A and B works out to -6. If you don't trust me, you can try it on your own. We're multiplying it onto -1, 0, 3. Okay. And then we're dividing it by the magnitude of B squared. So that's just going to be 1 plus 0 plus 9. And of course, normally you would you'd then square root those to find the magnitude, but since we're squaring it, that just kind of cancels out, and we are just left with so we're left with the vector 3 or 5. Oh, I should have put that over that. Textbooks often leave that symbol out, and it is important. I don't like that they leave that out. Okay, because otherwise it's just a coordinate. Oh, that didn't work. That looks worse than before. But there you go. So there's your scalar projection of A onto B. Okay. I'm actually going to leave the next 3 because they're all, it's basically the same idea. I'm going to leave all the next 3 for you to try on your own, and we'll take them up in class. Okay, so until next time, go Sabres.